Welcome to our presentation on Secure Code Vulnerability Scanner, LLM-powered SAST through prompt engineering. Let's explore how large language models can enhance static application security testing. Software vulnerabilities are a major cause of data breaches and financial loss. Traditional SAST tools face challenges like contextual reasoning, high false positives, and limited remediation guidance. Our project addresses these limitations by leveraging advanced technologies. Large language models, LLMs, offer advanced code understanding and reasoning capabilities. Through prompt engineering, we can guide LLMs to perform security-focused static analysis. This project explores their potential to accurately identify vulnerabilities and provide actionable remediation. Our research objectives include designing structured methodologies for security-oriented LLM prompting, evaluating multiple prompt strategies, assessing LLM capabilities in vulnerability detection, and positioning LLM-assisted analysis as a complementary tool in security testing workflows. Key questions we aim to answer include: can LLMs match or exceed traditional SAST in vulnerability detection? How does prompt design influence analysis quality? Can LLMs provide better context and remediation than conventional tools? Our methodology involves 4 prompt engineering strategies: comprehensive multi-layer analysis, few-shot learning with examples, chain-of-thought reasoning, and adversarial thinking prompt. Each strategy offers unique benefits for security analysis. Comprehensive multi-layer analysis involves a systematic, category-driven security review. It features explicit vulnerability categories, structured JSON output, and severity classification with CWE mapping. Ideal for full security audits requiring maximum coverage. Few-shot learning with examples uses example-driven pattern recognition. It provides vulnerable code examples with formatted reports, conditions models to recognize similar patterns, and uses a standardized reporting format, best for rapid assessments of common vulnerability types. Chain-of-thought reasoning is a step-by-step analytical process. It includes explicit reasoning stages, enhancing transparency and interpretability. This approach identifies vulnerability chains and design flaws, making it ideal for critical systems requiring deep analysis. Adversarial thinking. Prompt adopts an attacker-centric penetration testing mindset. It focuses on exploitation paths and vulnerability chaining, identifying high-impact systemic issues. This approach prioritizes real-world exploitability, suitable for penetration testing scenarios. Our experimental design includes 3 representative vulnerability scenarios: SQL injection, cross-site scripting, XSS, and multiple issues combining hard-coded credentials, SQLI, and sensitive data exposure. These test cases help evaluate the effectiveness of our strategies. Evaluation metrics include vulnerability coverage, severity accuracy, CWE mapping, remediation quality, and explainability. These metrics ensure a comprehensive assessment of the LLM's performance in identifying and addressing security vulnerabilities. Our results and comparative analysis show that different strategies excel in various areas. Multi-layer analysis offers comprehensive coverage, few-shot learning provides fast reviews, chain-of-thought enhances transparency, and adversarial thinking focuses on exploitability. Key findings in SQL injection detection reveal that all strategies correctly identified basic CLA. The adversarial prompt provided the most comprehensive analysis, covering multiple exploitation techniques, IDOR implications, DOS potential, and defense evasion considerations. In XSS analysis, chain-of-thought excelled at explaining data flow and trust boundaries. The adversarial approach identified exploitation chains, while all strategies recommended proper encoding and safe DOM APIs. In complex scenarios, comprehensive analysis identified multiple vulnerabilities. LLM-powered SAST offers strengths in contextual understanding, going beyond pattern matching. It identifies vulnerability chaining and provides remediation guidance with code examples and best practices, enhancing the overall security analysis process. The educational value of LM-powered SAST includes explainable findings, concrete attack scenarios, and learning opportunities for developers. Its flexibility and customization allow for adaptable prompts, evolving detection, and language-agnostic capabilities. Limitations and challenges include technical limitations like false positives, no runtime analysis, and limited context window. Practical considerations involve computational cost, expertise dependency, and tool integration challenges in CI/CD pipelines. Future research directions focus on technical enhancements like hybrid models, fine-tuned security models, and context expansion. Integration development includes ID plugins, CI, CD automation, and knowledge base integration for comprehensive security solutions. In conclusion, prompt design is critical for effective analysis. LLMs excel at contextual analysis, offering significant educational value. They serve as a complementary tool, not a replacement, working best alongside traditional security tools.
Okay. Hello, my name is Moawia Mahmood. I'm a software engineering student, and today I'm going to represent the final project of prompt engineering. Our project was secure code vulnerability detector. We have to make a prompt-based project in which we are going to add some code, and the code was supposed to show us the vulnerabilities and guide us through the process and tell us if there is any vulnerabilities in it, and then tell us about and give us any secure code examples. And so here I made this project using Claude. I just give it some data, not data. It's like I give it some prompt to tell it that the project must demonstrate the different engineering techniques for security analysis. It said to use a unique approach to guide the AI in identifying vulnerabilities by varying level of details and reasoning. So here I use four techniques or four prompt strategies: comprehensive multi-layer analysis, chain of thoughts, reasoning, few short learning with examples, and adversarial thinking prompt. So if we select any of these, here you can see that the prompt template is changes according to the prompt strategy. I will just represent the comprehensive multi-layer analysis and few short learning with examples. So if we see the comprehensive multi-layer analysis, if you look at the prompt, it says we have to analyze the requirements or identify all security vulnerabilities with high accuracy and calculate and like categorize it with the critical, high, medium, and low. And the output must be in this way. It must represent some like total vulnerability number, critical number, high, medium, low, if there are any secure code. Uh, so now let's have an example. This is like a SQL injection vulnerability, and if I tell it to scan it and tell us like if there is any vulnerabilities in this code for SQL injection, it will take some time, and then it will just give us the results. In this project, I use SQL injection, XSS attacks, and multiple issues. Here you can see the SQL injection report is here. The security code is 15. Its critical score is 1, high is 1, medium is 1, and low is 1. Yeah, I'm using. Okay. So the critical is the SQL injection vulnerability. On line 3, there is select from user where ID is user ID. In the description, it says the get user data function construct SQL query using string concatenation with unsynchronization user input from required parameters ID. an attack scenario. If you see a attack scenario, it says an attacker could send a request like get user one or one is equal to one, or get user one drop table user to bypass authentication, extract all user data to destroy database tables. So the secure code examples are this one. Missing input validation. It also says like attack scenario is like attacker can submit malicious payload, extremely large value, sample characters or script code as the ID parameter to exploit various vulnerabilities. Secure code example is this, so we can use this instead of line 7 to 9. We can use this to in our system to avoid the attacker. And if you see this is information disclosed through error handling. The attack scenario is an attacker could trigger database error through malformed input to gather information about table structures, column names, database types, and server configuration. The secure code example is this. We can use this code in our system to avoid line from 7 to 10. So here are some security best practices. Always use parameterized queries or ORM methods that prevent SQL injection. For the principle of least privilege for database connection. So now if I show you few short learning with examples, here you see the prompt changed. It gives examples like SQL injection, and then this is the prompt it gave. And first you have to analyze, and then example 2 is XSX. It will analyze this, and the example 3 is hard coded credentials. It will also analyze. This is a Python code. Before it was JavaScript codes, and the result must be in it must be a summary of telling vulnerability, total vulnerabilities, critical, high, medium, low security code. So now if we test the SQL injection for few short learning with examples, if it takes some time. So here the security code is 15, but there is only one critical issue, and that is SQL injection by string concatenation. And the attacker can bypass very close by using dump all the records to delete the user, and we can use this code in our system to prevent this type of attack. And here's some security best practices like always use it's the same thing but it's like less detailed because every prompt strategy uses different methods, and every prompt strategy is best for some specific criteria.